Okay, so we're about to start the second session of this conference, which is focused on physics application of machine learning. And we are now receiving Tracey, who is a senior research engineer at DeepMind in London. He received his Bachelor of Science in Engineering at the University of Rochester in 2008, and then a PhD in aeronautical astronautical engineering from Stanford in 2015, where he studied using machine learning techniques to improve turbulence model in low fidelity simulation. And he currently works on the control team at DeepMind, where he works to improve reinforcement learning algorithms with the focus of environments that are continuous and PD-driven. And he's now going to present us his work on magnetic control of nuclear fusion using reinforcement learning. So, thank you, Mehmet.
Thank you very much. Yeah, so first and foremost, I want to say that, well, I get to be the one who gets to give this talk in front of you all. This is actually the work of a lot of people, but you can see our full author list is very extensive. And while I did play a role in this, many, many other people have as well. And so I'd definitely like to acknowledge that this is not just me. This is a huge, huge effort that's been a long time. Great. So first, fusion. So you've heard of, say, nuclear power, nuclear fission, where we take large, heavy atoms like uranium and split them up. And fusion is the opposite, where we're going to try to take hydrogen molecules and push them together really, really hard. And in order to do this, you need to overcome the Coulomb barrier. And so you need to, first of all, get the hydrogen atoms moving very fast so they can collide at high levels. And they need to have many opportunities to do that, which means the hydrogen needs to be at a high density. And whatever you're doing needs to have a large confinement time in it. That means you need to keep the hydrogen atoms together in the same place for a long time. And so these factors combined be what we call the triple product. So temperature, moving fast, density, lots of them together, and confinement time, they have many opportunities to interact. And we want to push this number higher and higher. Now, when we bring the energy of a hydrogen gas up and up and up, it turns into a plasma state, which means that the ions and the electrons dissociate. And what this really gets us is something really nice, which is, first of all, the electrons are gone, so the ions can really fly. But also, now the plasma can sustain a magnetic field. And with this sustained magnetic field, that gives us a chance to control and manipulate that field. So even though we have temperatures of something like 100 million degrees, that would burn any kind of normal thing, what we can do is we can maintain this plasma in a vacuum and use a set of magnets to sort of compress, first of all, to make the density high, and also keep it from touching our device. One way of doing this is a device called a Tokamak, which has a toroidal shape of the plasma and kind of holds it there as this plasma ring in which the gas, really the plasma can be maintained. And so here's a picture of the jet Tokamak, which is at Oxford, and to give kind of a sense of the inside of the device and then also as a plasma gun. The work I'm going to talk about today was work done with the Swiss Plasma Center, and in particular the Tokamak à configuration variable, aka the variable configuration Tokamak. And this is really nice because actually for machine learning research, it's where it's there is it's able to be very flexible in the kinds of plasmas that it can generate, which means that it's very nice for doing plasma research, and it's very nice for doing reinforcement learning, so we can try to show many different things going on. And here we have various pictures of the TCB itself. First of all, situated in Lausanne in Switzerland, but also now a picture of the inside of the device and the building in its house. And because everybody loves good pictures, here's a picture of the plasma being in the TCB at once. And you'll see in a minute what this is a picture of. And again, just to give a little bit of sense of scale of the size of this device. So true nuclear production power plant Tokamak would be much bigger. But again, this is one geared towards research, geared towards trying many, many different plasma kinds to inform our future devices. And it's also really nice because it's also geared towards PhD students trying crazy things with it. So it's much more safe and hard to do anything truly bad to the device. So the way a Tokamak works is there's two sets of coils, control coils. One set of coils is to maintain the inner current of there's the current that flows through the plasma, and there's one set of coils that maintain that current. And there's also a set of control coils that allow us to manipulate and maintain the plasma. And so really, as it says here, there's two different magnetic fields, this toroidal field, and then the poloidal field. So in this, sorry, I'm doing really bad at talking about this. But anyway, the poloidal field is what allows us to manipulate, and with that set of control coils there. And in the end, there are going to be 19 different control coils that we're manipulating simultaneously, both to maintain this inner current in the plasma that maintains stability, and to do and then the other 17 coils to manipulate the shape, which allows us to change things like the density, the confinement time, or are called the strike points, as we'll see. So in general, what we're trying to do is this what we're called the axisymmetric equilibrium control. So we have the assumption and the maintaining in a tokamak that the plasma is axisymmetric throughout. So we're going to be showing many different 2D cross sections, and the way that the tokamak is designed also keeps this axisymmetric. And what we want to do is we want to not only maintain this plasma current, and we not only want to maintain the existence of the plasma, but we want to control many different aspects. Now, in the longer run, we'd really like to be able to control that triple product to maintain high density, high confinement time, and all these things. This is actually really hard to do for a variety of reasons, most notably because simulation and the science of it is really hard, which is one of the things that we're trying to develop at TCV, is understanding how different aspects of the plasma affect this triple product. In this work, instead, we're going to do the simpler problem of what's called shape control, which is maintaining the vertical position and the horizontal position of the plasma, but also controlling what's called the last closed flux surface, i.e. this black line that you're seeing around the plasma, and manipulating it there, as well as what's called the active X point. So this is kind of what's called the attachment point of the plasma in the device, as well as where these legs and strike points hit. And so in a full tokamak reactor, how many legs there are, where these legs impact, have a lot of effects on, say, the heat transfer from the plasma to the walls. And so you really want to be able to control these things. And similarly, the actual shape of the plasma itself has a lot of effects on things like edge localized modes and the density of the plasma and all of these things. And so at TCV, we're researching how these different shapes affect things. And for this work, we want to show that we can control and manipulate that how we would like. Great. So as an example, one thing that's really challenging, though, is that this is actually an unstable system. So we heard earlier today about these damped oscillators that stabilize down nicely, but this is the opposite. So in particular, this Z position, as the plasma, the Z position is unstable. So as the plasma gets more and more elongated, the Z position becomes more and more unstable. And so if you don't do any active control, actually the plasma is going to very quickly sort of expand either up to the top of the device or to the bottom of the device, and the whole thing is going to dissipate. And in TCV, this is kind of okay, but on the next generation of tokamaks, such as each of this being built, these disruptions can be very damaging because they're very energetic. And so we want to be very sure that we're not going to allow these disruptions to happen. But also the timescales are very fast. So this gives a picture of 6 milliseconds on how we're doing it, on the sort of scale at which these instabilities happen. And you can, in fact, do it much faster than that. We can assure you that. And so so we want to be able to control at these very high rates. And so we're going to manipulate these control coils at 10 kilohertz. That is, we're going to take actions 10,000 times a second in order to be able to maintain the stability. So, okay, so why would we talk about reinforcement learning? And why not just use traditional control? Well, there's a couple of challenges here. So one is that the way the traditional controllers work typically that you have to specify kind of exactly what you want to do. So first, we're going to pre-compute a feed-forward trajectory of how much current there should be in all of the coils at every different step of time. And then we're going to use feedback control to make the actual current in the coils be that way. Now, in order to figure out what the current in the coils needs to be, in order to do that, well, you need to have a model that says, well, what will the plasma look like if I have the current in the coils at this value? Similarly, each of these control systems is on its own hard. We need modeling for all of them. And we're going to pre-specify a specific set of coils to do each of the different control aspects we want. For maintaining the coil current, the plasma current, for maintaining the R and the Z position and the shape. And we need to design each of these individually. Each of these has independent knobs that need to be tuned. And we need to make sure that as we tune these knobs, we don't mess with the other controllers. So we're basically trying to force all of these different closed loop controllers to be orthogonal with one another, because otherwise the complexity gets too hard to manage from human control designers. So while traditional control techniques are very effective, they've required a lot of buildup over a number of years to get working in the first place. And second place, it makes them quite hard to manipulate and modify to do a completely new design just because of their sheer complexity. Whereas instead, in this work with reinforcement learning, we're going to remove all this complexity of all of these different feed-forward inputs, of having all these independent controllers, and instead we're going to work on let's tell the reinforcement learning system what shape we want to make. It's going to figure out how to manipulate all the coils to do that. So instead of having all these independent boxes that need to be independently tuned, we're just going to say, here's what we want. Please find us a solution to get there. And so we're going to have one controller for all 19 coils at the same time. We're not going to use any of these feed-forward generations. And what I didn't mention on the previous slide is that if you want to do shape control on a traditional controller, you need to have feedback about how wrong the shape is. On the one hand, that's kind of fine. But on the other hand, it means that you need to be able to estimate at 10,000 frames a second how wrong your shape is. And it actually required a lot of effort for them to make a feedback controller even possible on this system. Whereas in our case, we're going to basically push all of the complexity of the reconstruction into the agent itself, and it's going to learn how to do that on its own. So it's going to learn how wrong its own shape is from the measurements directly. So for those of you who might not be familiar with reinforcement learning, it's kind of a different branch of machine learning. So as we've seen already today, there's many supervised learning examples where we're trying to predict inputs from a set of outputs. And we've also seen some unsupervised learning examples where we want to do things like classification and clustering in order to understand what our data looks like. In reinforcement learning, we're basically going to teach a system how to work through interaction with the environment. And so it's going to learn through trial and error. And one thing that really separates reinforcement learning from more common, say, supervised learning approaches is that the agent needs to generate its own data to figure out how to do well. So the first time an agent interacts with the environment, maybe it does really, really poorly, and you say that was a bad job. Well, the next step, it needs to figure out how to do something different to try to do a better job. And so it needs to both understand what it means to be good, which is kind of like in the supervised learning case, but also understand how to generate data to make sort of good trajectories and good outcomes exist. And so trying to generate this feedback loop and do this feedback loop correctly is sort of what reinforcement learning is about. And in particular, we're going to have this agent environment interaction loop where the agent is going to, at every time step, the agent is going to take an action. The environment, which for now is going to be sort of abstract, we're going to eventually see it's going to be simulation, but then we're going to run on the real Tokamak. And so in that case, the environment is going to switch, or be either of these really. And on the outcome, the agent is going to get a whole bunch of observations about the state of the world. And during training, the agent will also see a reward, which is defined by us as to how good of a job it's doing. So the advantages of reinforcement learning over the more traditional methods, right, are that it can really take advantage of very heterogeneous inputs. So it can take binary inputs or continuous inputs, and it can have a very high flexibility in the reward. So in traditional control, it always works off of an error signal. Usually, so that's not say always. It often works on an error signal where you have to explicitly say you want the number to be 2, but it's actually 2.5, so please adjust. Whereas in our case, we can define much more vague reward functions. But on the flip side, this is also a downside because, as we'll see, the agents can also be very clever in getting a high reward while still not doing what you want. But the other main advantage in this case is that we also can learn to control nonlinear stochastic dynamical systems, which when we combine the fact that plasmas are very hard to model explicitly, and also the fact that traditional typically has to learn around a linearization point, whereas if we want to manipulate the plasma in many different formats, that's overall going to be a very nonlinear system. So in a traditional case, you might have to do many, many different linearizations and control around each of those. In our system, we can learn one integrated thing for that fully nonlinear dynamics. So reinforcement learning in general, I probably don't need to tell you, but it's been used in many cases. So if we think of this AlphaZero work from DeepMind, like the reward signal was, did you win or did you lose at chess, Go, and they didn't even need to know an explicit sort of environment dynamics. The agent figured itself out what the rules of chess were while it was playing, and then also how to be very, very good at chess, only from the signal of did you win and did you lose. And similarly, we see that the input space is very discrete. Like where are the pieces, which pieces are they, on what points are they on? And same thing, the action space is very discrete, which is which piece you're going to move where. On the flip side, we take something like this work from OpenAI. I'm using a humanoid hand to solve the Rubik's Cube, where here there was a visual input. The outputs themselves are very continuous. And then we have something like the StarCraft work, Alpha Star from DeepMind, where again, there's very, very many different kinds of inputs and a very complex output space. And reinforcement learning is able to work on all of these domains, which is one thing that makes us at DeepMind quite excited about reinforcement learning and the future there. So just some fun videos of how this can work. So here we have a quote unquote humanoid walker, and its reward is to see how far it can move in the space and quickly. And after a couple hundred trials, it's really not doing very well. It barely can stand up. I mean, let's be honest, it can't even stand up. If we let it run for 2,000 trials, it's able to start moving forward, and it's at least able to make it off its first plank, but then once the terrain gets to be a bit tricky, it fails. We move forward with training. Now at 6,000 trials, it's all of a sudden able to start jumping and understand how to move. 8,000 trials, it can jump over small walls, and it's fairly impressive. And then finally at 15,000 trials, it's able to move very quickly over sort of very different heterogeneous environments. And so this gives a sense that even with a simple reward function of get farther in the world, it's able to learn very complex behaviors. And this work is from 2015, and all of these things have gotten so much better since then. And that's one of the places where we started to see, oh, maybe this is now ready for the real world. So great. So I told you in general about reinforcement learning, but what do these components look like for the Tokamak system? Like what are all of these things? So as I mentioned before, an environment mathematically is something that can give the agent an observation and also return a reward. So in the real thing that we want is we want to run on the Tokamak and control a bunch of things. And our observations are going to be a set of flux loops and magnetic probes, which are both sort of two different measurements of the state of the magnetic field in the Tokamak. And we're also going to measure the current and it should be 19, sorry, of the control coils. Oh, sorry, okay, so there's 19 control coils, but there's one redundancy measurement between two of them, and so we're going to observe all 20 of those coil current measurements, even though there's only 19 of the coils. One thing that you'll notice that's not here is that we can't actually directly observe the plasma. We can only observe the magnetic field. And so the agent is going to need to be able to infer, given that this is the state of the system, what does the plasma actually look like? And when we show you videos in the future, so the agent itself is one way of doing this, but there's also a sort of more first principle scientific way where they can find a reconstruction of the data. So in the future, when I show you videos of some of the videos are optical, but any of the non-optical videos that I show you are going to be reconstructions of what the plasma looked like, essentially doing a complicated least squares, physics-based least squares of what the plasma must have been in order to generate those measurements. Now, in practice, we would love to be able to learn on the Tokamak itself, but this is just totally impossible. So first of all, it's an unstable system. So if you have your agent who's never seen a Tokamak before, it really loses the plasma in a couple of milliseconds, which even at 10,000 frames per second, 10,000 actions per second, only gives you like 20 or 30 data points, right? So it'd take forever in order to learn a reinforcement learning system from scratch. Similarly, the Tokamak discharge, even if you're doing really well, only lasts about 2 seconds. And actually, through the whole course of experiments writing this paper, we had less than 2 minutes of actual experimental time on the total Tokamak for all of our experiments doing everything. And unfortunately, today reinforcement learning is still very, very data hungry. So this is just totally a non-starter for learning on the device itself. So what we're actually going to do is we have a simulator that's called FGE, which stands for the forward graduative evaluative, meaning that it's a model of the plasma, which is the Grad-Shufanov equations, which for those who don't know, basically it's for reinforcement learning purposes. This is a very expensive environment to run on. So the previous Walker experiments I showed you, I don't know the exact numbers, but it's maybe like 1/100th of a second per step, whereas this is more like 2 seconds per step. But from a plasma perspective, these Grad-Shufanov models are very, very simplistic and are sort of as simple as they need to be in order to do this plasma shape modeling, but no simpler. And so basically the system is this Grad-Shufanov's equations for how the plasma manipulates, plus these circuit equation solvers to model a coupling between the control coils and the plasma itself. And so to be a little bit more simplistic, right, the plasma is manipulated by these control coils because it has an internal magnetic field. And similarly, the internal magnetic field of the plasma influences the control coils back. And what this simulator does is simulate how the magnetic field evolves in time as a combination of applying voltages to the coils to manipulate them and those coupled interactions with the plasma. Great. And what this simulator does then is it simulates, given the voltages we take, what are the observations we're going to make? And so just to say, right, it's not like I promised kind of at the beginning that we have this nice fully integrated system, but it's not true that we're getting rid of physics and we're not getting rid of the need for the understanding of physics, right? Well, all we've done really is we've pushed the complexity from sort of real time to do these traditional control really, really fast, to instead we're pushing it into a simulator where we can run this many, many times offline in a computer experiment. And then what we're secondly going to do is have the complexity of now, given that our simulator has only seen, given that our machine learning agent has only ever seen simulated states, how do we get it to run on a real Tokamak? And in the end, what we're going to do is what's called zero-shot Cinderella transfer. That is an agent that's never before seen any real hardware data, and we're going to run it on the hardware anyway and get it to work there. Great, so what are we actually trying to do? Well, the first thing that we want to do is we want to keep the plasma alive. And so what we're going to show now is one of the first videos that we ran on the Tokamak itself. And this is 0.024 seconds of real time. And we see that our very first experiment that we ran, surprisingly, you can really, really see right there that wobbling from the unstable oscillation, and it loses it. But we managed to figure out a whole bunch of things that were wrong between the initial result and this result here. And now we're watching something that's a half a second of real time. And sure, it's a little bit wobbly at the beginning, but we are very, very excited to see that it's actually able to hold the plasma together for a half a second shot. And this half of a second actually was only there because for this particular experiment, it was set to cut off after a half a second. So the agent was able to stabilize for the full window that we gave it, which was very exciting. The next thing that we try to do is, rather than just keep the plasma alive no matter what, we want to stabilize the location of the plasma, that is the R centroid and the Z centroid in the place. And so again, here's another experiment at a half a second of real time. And here we go. Now, on the one hand, I'm going to say, look, great. Look how stable that R and Z position are. This is sort of exactly what we told it to. This is great. Many of you are probably thinking, but wait a minute, didn't it just like totally manipulate the shape there? And this goes back to what I said before about the blessings and the curses of reward functions. So actually what happened is the agent said, you know what? These really elongated plasmas are unstable. The best way to maintain a stable R and Z position is to actually decrease the elongation. This totally removes the instability from the problem, and therefore the agent is able to keep it there and keep it there extremely steady. So the agent basically found the box and said, you know, the hard part of the problem is the instability. I'm just going to remove the instability and then control there perfectly well. Which on the one hand is exactly what we asked it to do. On the other hand, from the perspective of generating plasma energy, higher elongated plasmas are much more interesting because they sort of you get much more plasma for the shape of the tokamak that you're building. And so this in the end isn't what we want. So now that we know that things are working, and actually our agents are even finding surprising solutions to start, now we want to maintain this full shape control of the tokamak. So as I said, we want to maintain all of these things simultaneously. We want to have, the tokamak itself is about 1.2 meters tall. It's like, I think it's a half a meter wide. And we want a total error in the position to be less than 2 centimeters. And we want the total error in the current of the plasma to be less than 5 kiloamps, which sounds like a lot, but the actual plasma current that we're targeting is on the order of 150 kiloamps. So it's within a couple percent of the actual target. And in addition, what we're going to do is we're not just going to maintain one static shape like this image shows, but instead we're going to give the agent a full time trajectory of what it should be doing. So at every millisecond in time, we're going to give it values for all of these quantities to control, and then we're going to try to see if it does that. But until we get there, let's now talk about the agent and how we're going to do the training. So now we know what we're training on and what we want to do. How do we actually do that? So the agent is basically the other half of this thing that takes in an observation and a reward signal, and then it's going to output what actions we actually want to achieve. And our goal is we want to find the optimal policy, and we define optimal policy by maximizing the discounted sum of future rewards. So that is, given the state that we're in, which is the observations, and in our case, the targets of what we want to achieve, tell me it's going to output an action to achieve. And in the particular way that we're doing this, at every step, actually, the agent is going to output a distribution of actions. And this distribution of actions is first going to allow it to explore, and while it's doing the training, to try different things. And then when we deploy it on the actual tokamak, we're going to take this, in practice, this is going to be a Gaussian. And so we're going to take the mean of that Gaussian when we actually deploy in the tokamak to make sure that we know what we're going to be trying. And so this particular reinforcement learning algorithm does is it's going to be working on this Q function, which is the discounted sum of the prediction of the discounted sum of rewards given a particular state and given that an action that you're going to take. And we're going to be modeling this Q function over time. So to put it a different way, what we would really love to have is access to the optimal Q function for the optimal policy, right? So what we really want to know is, given what I'm about to do and what the world looks like, what is the best thing for me to do? And the Q function is a representation of that. The Q function says, given where I am and the action I'm about to take, how well am I going to do in the future, given the policy that given the policy that I have? Now, if an oracle tells you, here's the Q function for the optimal policy, then it's in a sense easy to derive the optimal policy itself, because you can just say, okay, given where I am, over all of the actions I can take, the Q function is highest here, so I'm going to take that action now. But the challenge is you don't actually have this optimal Q function. Similarly, if someone were to say this is the optimal policy, and again, in a sense, not that hard to find the optimal Q function, because you can run your policy many, many times and find what the Q function is. But again, we don't know the optimal Q policy. We don't know the optimal policy. So in reinforcement learning, we need to figure out both what should we be doing right now, and how good is it to be doing what we're doing right now. And these are the objects that we're going to be working with. Now, there are kind of two different ways to do it, which are reminiscent of what I just said. So one method is to work on the Q function and have the Q function be the only thing we care about. And so as we get more and more data, we're going to explicitly model the Q function. And in deep reinforcement learning, we're going to model the Q function with a neural network. And then we're going to implicitly derive our policy from the Q function, say by doing greedy exploration, where some percentage of the time we're going to take the optimal action, and some percentage of the time, we're going to do a non-optimal action uniformly at random. Or you could use some kind of softmax thing that says, given all the actions and the Q function that's there, I'm going to take something proportional to how good the Q is. Another way we can do this actually is we can do what are called policy-based methods, where instead of the Q function being the primal object, we instead have the policy being a primal object. So our neural network is going to tell us, here's what the policy is, and then we could say update an implicit estimate of the Q function by if we look over full trajectories, we can update our policy based on which trajectories had high reward and which trajectories didn't have high reward. And so to reiterate, in this case, we were explicitly modeling the Q function and implicitly modeling the policy. In policy-based methods, we're explicitly modeling the policy, but implicitly modeling the Q function for these updates. What we're actually going to do from this work is we're going to use actor-critic methods, where we model both of these things at the same time. And this has a couple of advantages. So to reiterate, we're going to have one neural network that models the Q function, and it learns the Q function based on the data that it's getting from interacting with the simulated environment. And then we're going to have a second neural network, that's the policy network, that tries to match the policy with what the critic says a good Q function is. Or another way of saying it, the policy tries something, and then the Q function of the critic that says that was good or that was bad. And similarly, the critic is also watching lots and lots of stuff to see what's good and bad. And this has advantages in terms of stability and being able to train for continuous spaces, definitely, and especially high dimensional spaces. But another really important thing for this work is that it allows asymmetry between the two actor-critic networks. So in particular, the actor network that outputs the policy, that needs to be able to run real time on the plant, and therefore needs to be really fast, needs to be able to execute at 10 kilohertz. Whereas a critic policy actually can be a really large network. In this case, we're going to use an LSTM core to model all of the long-term dynamics. And the critic cannot run at real time, but it also doesn't need to, because the critic is only telling us what's good and bad. And by the time we're actually running an experiment, it's too late for that. We just need the fast part to run. So we're also going to really take advantage of this asymmetry to be able to run. And in particular, the actual algorithm we used is something called MPO, which is a specific version of how you do the updating of the actor network and the critic network. And MPO has a lot of benefits. It's kind of like TRPO, if you know, or PPO, for those of you who know. That is, it has a trust region of data where we think, okay, in this region, we like the data from our networks, and we're going to slowly modulate our networks over time based on new data we're coming in, but not allowing them to move too far, which really helps stability. And it's also really nice because MPO is very data efficient for a reinforcement learning algorithm, which is very beneficial because, as I said, relative to normal reinforcement learning, our environment is very slow. And so we really need to be able to use these off-policy data efficient methods. And in particular, MPO works really, really well for continuous action spaces. And in our Tokamak problem, it's a totally continuous observation and action space problem. So in general, the way that this procedure looks like is we're going to have not just one, but many, many different interaction loops between the simulated environment and our control policy at the time. And in practice, we're going to be running 5,000 different instantiations of our simulator. And all of these things are running and generating data. This data is going to be fed into a replay buffer. And this replay buffer is basically a first in, first out queue that's going to maintain a history of recent data. And then our learner, which is updating the Q function and the policy, is going to be sampling data from this replay buffer and again updating the policy. And then as the policy gets updated, that new policy gets sent to our interaction updates, and then this runs. And we let this run until we're happy with the policy, which in simple cases is going to be something like 2 or 3 days. And in complicated cases, it's going to be more like 2 or 3 weeks. And as I said, these algorithms are very data hungry right now. It's one thing we'd really like to improve, but that's where we were. And then now that we're happy with the policy, we're going to take only the actor network and compile it down into a binary. And then we're going to take that binary and actually execute it on the real TCV Tokamak in Switzerland as part of their control system. And then just to show why this matters for this asymmetry in the actor critic, if we look here, for instance, the blue line is kind of what we actually train on, where our critic network is able to have an LSTM to help it understand the time dynamics of evolution. Whereas this orange line here, for instance, is the actor network that we run on the panel, which is able to run at 10 kilohertz. So if we are allowed to have the actor network be really small, because it's able to learn from the good value that's in the critic. But if we were constrained to having only the actor network there, having both on the actor and the critic side, then the whole system really, really struggles to learn and generate good quality results, even on simple cases. So the fact that we're able to exploit this asymmetry is really important. Now, I also said that typically we train for like 2 to 3 weeks, and these are all very data inefficient, and it is one thing we like to show, but I'd also like to point out that we were really optimizing for making our learning be as fast as possible in terms of wall clock time. But there's also a fairly sharp trade-off between sort of wall clock training time, and even if you can reduce the number of actors by a factor of 50 or so, and only lose a day or two of training. So this is something that we're still exploring, is how to make like 5,000 actors or make 20 simultaneous actors be just as efficient as 5,000 actors. Great. And so now the last thing to talk about before results is how do we actually get the zero-shot Cinderella transfer to work? So one thing I want to say is that while I get to talk about the fun science, there's lots of work that went into the engineering details to kind of make this whole procedure work in the first place. And I'd like to put a shout out that actually between running the first time and getting something that basically did like what we thought it should do, only required 4 or 5 experiments on the Tokamak, which just goes to show how good of a job everyone involved in the engineering side and making all of that consistent, like all of that just really worked, and it was very, very impressive. Now, after the first thing kind of worked, we had to iterate a bunch in sort of a meta loop on how to change the training to make this right. And so one of the things that we did was we introduced targeted variation in the environment. So changing the sort of the parameters of the plasma that can't be modeled from first principles, but are instead inputs to the simulator, changing the variation of those. We had quite a bit on modeling the power supply dynamics and adding stochasticity to how the actions are applied and all of these things. We also upgraded the simulator because there were aspects that the agent was doing the right thing, but the simulator was doing the wrong thing. And so we changed the way the simulator worked to manage. And then we also did things like, in the simulator, there are ways that you can really throw the plasma across the whole device in like 1 millisecond or something. And if you move the plasma slowly, the simulator is a very, very good simulator. But if you move the plasma way too fast, then all of these things kind of get a little wonky. So we also did things like make sure the targets aren't changing too fast, or make sure your reward functions, like if you just do the naive thing, which is say make this plasma shape, and if you're minimizing the discounted sum of rewards, the agent has incentives to move it as fast as it possibly can in the simulator. But this also is really, really bad for transfer. So making sure that we don't have really stupid reward functions that sort of beg the agent to take advantage of the deficiencies of the simulator. So basically, there's a combination of changing the simulator, adjusting the rewards to do what we want, and then also making sure we have the right kind of environment variation to make sure we're both able to still learn good policies. Because too much variation means you can't learn anything useful, but not enough variation means that the transfer doesn't work at all. Great, and so here's now getting to the fun results. So this is what we call the demonstration shot, which is to show here's that we can do every part of the main plasma experiment that you would want to do. So when this loops, first we're going to be handed over the plasma after the initialization phase. So it's about 80 milliseconds into the shot, where there's kind of a control system that we're not dealing with that kind of creates the plasma from nothing and gets it up to something that even is controllable. Okay, so we don't do that part yet, but once a plasma exists, then they're going to switch the control to us. We then ramp the current up in the plasma from about 60,000 kiloamps all the way up to 150,000 kiloamps. We then show that we can elongate the plasma to useful shape. Then we can shift it down in the device. Then we can do what's called diverting the plasma to keep it off of the walls in the middle of the shape. And then finally show that we can bring it back up to a safe position and dissipate and reduce the energy in the plasma down to a safe level before we let the plasma dissolve on its own. So basically showing that we can grab after initialization, control it to a shape that we want, and then safely dissipate it so that you don't do any damage to the device. And so what we're seeing here on the right is these blue dots are where we wanted it to be. All the colors are then a reconstruction from the real measurements on what the plasma array looked like. And then here we're seeing an optical view of also what's seen. And so here what we're seeing is you can see this straight point here that's kind of going around the device, and you're seeing the legs. Because really, again, you can't actually see the plasma. You can really see gradients in the plasma. And this is then just kind of a different time slices of all that we were doing and different time traces. And you can see an extremely good match between the plasma current that we commanded and the plasma current that we received. And similarly, we were very good on the Z location and the location of this X point. We were trying to explicitly control it to various places. Now that we had done this, we also wanted to show that we could do many, many different shapes. So here's a number of different kinds of shapes that are each on their own useful for devices, for plasma research. So in particular, this shape up here is the proposed shape for the ITER tokamak that's coming. This one here is what's called a negative triangularity shape, which has lower production of something that are called ELMs, which are problematic for having heat sort of burnt out at the wrong times in the plasma. So this is a potential shape for the future. Similarly, this is a snowflake shape where we see there are many legs that divert the heat to a number of different places. Rather than having one part of the tokamak that receives a lot of heat, maybe you can spread it out. And then lastly, we showed that we could do something that's called a droplet, where we have two different plasmas in the domain simultaneously. Now, it's probably true that you could do this with the traditional control, but in order to do this, we would first of all need a new simulator that could simulate multiple plasmas. Okay, we needed that too. But then you need to figure out how to make it fast, so you're doing it at 10,000 frames a second. You need to figure out how to tune all these control techniques. You need to figure out how to do all these feed forward current generation, all these things that we need in the traditional sense. And no one's ever done a droplet before, so you'd all need to redo this from scratch. Instead, what we did is we changed the reward function to say before you wanted R and Z of one thing, now you need R and Z of two things, and then we just run it. So this kind of shows the major advantages. And this is the first time anyone has ever sustained a droplet on a tokamak. And we were able to control both the current and the location, which we're very proud of. So to summarize, basically, what's really nice about our approach is we have a single reward function where we get to specify what we wanted. Although we also found, right, as a downside, right, is that we did do a fair amount of tuning of all the different techniques. Like we wanted to control the current and the shape and the X point. We did do a fair amount of tuning to get those things to be balanced. We also were able to do the whole control thing in one integrated loop, getting the domain knowledge from the simulator, but not needing any sort of real-time execution. I think the benefits of traditional control that we don't have at the moment are a clear relation between the parameters, right? So maybe you have the integral gain controller that an engineer just knows what that tuning means, whereas this kind of tuning doesn't exist today for reinforcement learning. And similarly, you can do things like make sure that the error is approaching zero as time goes on. Whereas in our implementation today, basically if the agent's like, I'm doing well enough, I don't care if I'm off by a half a kiloamp or 0 kiloamps, they all give me a high enough reward, so I'm okay. So these are things that we'd like to improve in the future. And so, yeah, in general, I think we're really proud of this work because we think it's one of the more complex places where reinforcement learning has been applied to a real problem. And it's true that in this particular domain, traditional control is already really effective, but we think RL has a number of interesting advantages here that we were able to demonstrate, and we're hoping to push these forward both in the plasma domain and otherwise. And another thing that we're really excited about is this also has a potential to do what's called co-design, right? So if you propose a new tokamak shape, you can run a controller and kind of see how well that tokamak system will go. And even if in the end you want to use traditional control for its advantages and stability and understandability and things, you can still use reinforcement learning to understand what a controller could look like, and that's very, very automated. And so you could run these design loops. And yeah, so we think it has a very bright future for RL being used in the real world. And lastly, I'd like to say that this is a very successful multidisciplinary collaboration, which I think is especially important for here. Like, there were many times where our agent was doing something wrong, and I can say, no, like your simulator is fine. This is our agent doing something stupid. Let me fix the way that this training control works. There are other times where they were able to say, no, the problem is that you set RP to 5 times 10 to the 6th, and it should be 4 times 10 to the 6th. Let's fix this in the simulator. So being really able to do this multidisciplinary collaboration was very important and have a very tight coupling. And so I think it also shows kind of the benefits of these true multidisciplinary collaborations as we want to bring machine learning approaches to these more like scientific and from my perspective, real world domains. So thank you all for listening. I'm happy to take many questions.
So everybody has some questions in the room already. So you guys one here.
Thank you for the interesting talk. Just wondering how do you optimize the parameters of the model given the simulation? That's it. Takes a long time for the training.
Yeah, so as I mentioned, we have that 5,000 replicate copies, and those run together, and those generate data. So in the very beginning of training, basically every time the agent runs, it loses the plasma because it doesn't know how to do things. Then slowly it learns, oh, if I take this set of actions, I can at least maintain the plasma alive. And while maybe I'm not getting a high reward, I'm at least not getting hit by a stick every time I lose the plasma to a disruption. And then over time, through this iterative procedure and by running this MPO algorithm, it slowly learns what a really good shape looks like and how to match all the target parameters. One thing I didn't say that I should have said was for all the results we've shown, it was one integrated control policy that ran that whole discharge. So it did all those things once in one policy. However, for each experiment, we had a different agent that was trained. So that particular agent that we ran kind of only knows how to make that one time trajectory of shapes. And making something that kind of is able to do all shapes with one agent is something else that we'd like to explore further, but it's not where we are yet.
Anybody else? Oh, we got one from Zoom.
Thanks. So I have a slightly more general question about reinforcement learning in science. At the minute, a lot of reinforcement learning is quite sort of theoretical and theory-based research. And this is a fantastic example of applying that in a real-world scenario. Do you have any sort of thoughts on the challenges for getting reinforcement learning into more sort of actual research and applying it to different problems, and particularly scaling for researchers who maybe don't have huge compute farms?
Yeah, I think there's a couple aspects to that problem. So one is on the research side, and something we struggle with is like we're also on the research wing of DeepMind. DeepMind's a research organization, and so we look for RL problems that are both interesting in terms of what they could achieve, but also ones that are interesting for research, right? And so part of the reason we chose this is we thought that it would force us to figure out how to do things like have more efficient reinforcement learning algorithms. And so like, while we're not there yet in terms of something that just a normal person could run, if we could take that 5,000 down to something like 50, which we're starting to work on, right now all of a sudden that is accessible to someone who has like a normal computer. So while it's true we do use a lot of CPUs, the actual learning side of it was only done on one TPU. Which is something that's accessible to a normal person, or I mean, you could probably do it with one GPU, so that's there. So one answer is like we partly chose this problem to try to address this other problem of how do we get more efficient learning. And so while it's true that this is not particularly efficient yet, it's still relatively efficient to something like StarCraft. And then I think the second thing that's a big challenge is because of this data hungry nature right now, you really need either a good simulator or you need something that's like really cheap to replicate in the real world. So like there are some places that have maybe an ARM farm where you have a couple hundred of actual things, and there you can do learning from scratch on hardware, but otherwise you need a good simulation to start. And while we're getting better at doing sim real transfer, at least for me, I'm always worried the first time because we know these reinforcement learning agents are really good at picking up on really bizarre quirks of your simulator. So I think that's the other challenge with getting reinforcement learning to the real world is because of these data efficiency problems, it's hard to find places where like you have a simulator that's good, but it's not good enough for traditional control or whatever. And so I think one of the more pressing research directions and one that we're trying to accomplish is, yeah, how do we solve this data efficiency problem? Because it would open it up for so many more domains.
Peut-être another question in the audience.
Thank you for your talk. I have a question regarding the reward function. When you are training your models in the computer, you can precisely calculate the geometric parameters. But in real world, you did mention you cannot really calculate it, and you only have some observations related to the currents. And how did you deal with the reward in the real world case?
Yeah, so it's a good question. So when, as you said, when we're doing the training, we have access to the actual real shape. And so while we're doing the training, at every step, we do in fact have the reward, and the agent can learn from that. So that's where the learning from the simulation is partly to understand the dynamics, but it's also to understand the reward. When we run on the real plant itself, you don't actually need to compute the reward, because at that point, we're already running our pre-trained policy. So it just needs to know how to act. It doesn't actually need to know how good it's doing at that time. So then there's the second question, which is then how do we figure out if it's doing a good job? And that's through this reconstruction that I mentioned on the way they reconstruct, and it actually uses, in a sense, it uses the same physics equations as the forward simulator. So basically, you don't need it while you're running on the fly, but you can calculate it then post facto. And another thing we'd really like to do is figure out how can we bring in small amounts of hardware data to improve our policies there. And if you want to do that, now you need to do exactly as you suggest, which is sort of maybe you still can't do it online, but again, afterwards you could do these reconstructions, see how the reward function really was as a function of these measurements, and maybe tune your policy that you've mostly trained from the simulator that augments it with real world data to make it even better. And that's something we did not do in this work, but we really would love to do, and it's something that, yeah, just feels like it should be done.
Thank you very much.
Hi, so thanks again for the great talk. I was wondering if you could speak to the reward function shaping. So for instance, it's a little bit, as you were saying, it's a dark art as to how to best shape the reward. And really, as we've seen in other works, it's the case that agents can exploit this. As systems become more complex, do you feel that it's going to become more and more of a craft as to how to best create a reward function, or do you think we should be moving more towards understanding and explaining a little more how the system should work in a more explainable way, rather than sort of trying to hack the reward function as much as possible to a single value that encompasses everything?
I'm not sure. And genuinely, I'm not sure, because there's a bunch of different things that seem to be happening that all sort of move at this, right? So on the one hand, you have things like alpha zero that just like, we just throw everything away, we give it a nice simple reward function, and all of the complexity that you want emerges because we have an algorithm that has a good exploration policy and is able to figure out all of these things. I think our problem is somewhere in the middle, where we try to design reward functions that kind of have these nice global, not literally convex, but kind of allow the agent to funnel into a bowl, right? That's kind of where the, I don't know what to call it, the science of design, but the art of reward design is coming up with kind of reward functions that are globally useful and all this stuff. On the flip side, though, if you take a look, you have things like DALL-E that's coming out, and things like like where you're able to craft an image from text, or if you're able to, and that's going to start moving to videos, and it hasn't already, right? And those things are a way of now maybe you can move to like a person specifies in text what they want. Now you have another system that kind of then generates what trajectories look like. That then maps to some kind of trajectory-like reward function that then maybe our internal system wants. And so I think to put all these thoughts together, I think both we're getting better and better algorithms at solving generic MVPs that are able to do better exploration, are better at encapsulating things like, I don't know about in the sort of like the fully continuous space, but if you look at things like object manipulation, right, things that are really able to learn what objects look like while they're also optimizing MVP, right? So we're getting better at exploration, we're getting better at kind of automatic environment segmentation, but purely from an MVP perspective. On the flip side, we're also getting way, way better at circumventing, like, here's what a person says they want, and let's make a thing that looks like what they want. And now you have like an automated, highly fine-tuned reward function that's now maybe easy, where you don't need to solve an arbitrary MVP. You actually have already given it the local minimum to find, and now it's really easy to solve from that. And so that's kind of the exact opposite, where maybe we should go into like even more finely specified reward functions as long as we have a better way of generating them. So I think the field is kind of, I don't want to say bifurcating, but because advances are coming so fast, it's really hard to see how this is all going to play out. So I can see multiple solutions to getting effective solutions fast.
Thank you.
Okay, we have, I think we're gonna like one more quick question because we're gonna need then to go to the next talk. So
I'm curious about the sim to real. So I'm not sure I quite got it. It's you're randomizing some of the parameters in the model, and as you train on slightly different versions of it. But you said there, I think you mentioned there was some kind of like tuning you did of maybe the amount of noise you're adding, or I'm not really sure.
Yeah, so and so from the start, we've always had things like measurement noise and things like the noise, like how much noise the action also has. So if you command 5 volts, you might actually get 5.1 volts or something like that. Then in the next iteration, we added plasma parameter variation, where at the beginning of each episode, we would sample what is the plasma resistivity, what is the plasma mutual self-inductance, things like that. And you really want that to be some sophisticated time varying model, but that's really hard to do right. So we just kind of have a bunch of different sampling, but it'll be at the start of the episode and then held fixed. And then we also did things like, it turns out that power supplies are really, really complicated and they didn't work at least how I thought they worked. And it's very hard to model that. So we instead modeled it as a pure time delay, but a pure time delay with some randomness such that the agent can't exactly rely on when I say it's 10 volts, it's going to really be 10 volts like half a millisecond from now. So that gives a sense of the environment variation we did. And we had a little bit of meta loop around it where we ran an experiment. We had the self-inductance somewhere between 3 times 10 to the 6th and 9 times 10 to the 6th. We ran the experiment and we saw that we needed to shift it and shrink it a little bit or something like that. So that's kind of where some of the meta learning comes around, how we fed experiment data back into an agent, even if it wasn't for any specific agent.
okay, so we're gonna move to the next talk, and I'm sure Dr. Tracey will be happy to answer questions during the poster sessions later. So thank you again, totally interesting.